Cast is now starting. All attendees are in listen-only mode.
Hello, welcome to this ADIS webinar on why time is critical now. Time has become a critical factor in support of many industries, and we have a set of panelists, as you can see on the screen, and we'll introduce them as we go through. My name is Mark Weiss. I'm the moderator for this webinar. I'm a consultant with my own company, Mark Weiss Consulting. And I'll begin. There are a number of factors that are critical for time. And there can be a little delay, and there it goes. So the first slide shows kind of an overview of why time is critical now. I present four general factors on this issue. One is because time enables position and navigation. Time is a major factor in supporting distributed data systems and computing. The electric power smart grid requires precision timing to operate optimally. And timing also simplifies the flow of data with a combined flow of data and timing. Position and navigation are so position and navigation depend on synchronized time from known locations. That is, you like GPS. If you know where the satellites are, you know when time leaves the satellites. They're synchronized, and the signals traveling through the air travel at a foot per nanosecond, so that nanoseconds now become extremely important. But radio signals traveling through the air are impeded by reflections and trees and even air. The ionosphere and troposphere in the air can impede these signals. Next slide, please, Katie. So a second major factor is coordinating distributed databases and distributed computing. So this is another growing need as we have many systems that are distributed around the world, and there are many kinds of databases around the world. Many people are getting online, and there are many online services, and you have a database in New York, you have another database in Hong Kong, and these databases the data has to be synchronized, and timing is a critical enabler of this. Another major use of timing is the 5G radio services. Accurate timing is becoming more important, and tighter timing is a new requirements are coming with the 5G radio. So timing simplifies the synchronization of data. The other major issue is what happens in the network when there's a problem. Traffic control. If there's a failure somewhere and there's this domino effect throughout the network, how do you find where did the root cause happen? Time synchronization is also essential for distributed processing and control of systems. So the electric power smart grid is often just called the plain old smart grid. This is critical for time. Synchrophasers is one particular piece of the technology that are essential for preventing failures in the smart grid, but they require multiple differently routed sources of time. So there are, GPS is not enough for them. They need to have time supplied in multiple ways in order to be extremely reliable. There are also these intelligent electronic devices, sometimes called IEDs, and they need precision timing, traveling fault wave detection. If there's a fault in the line and the fault travels across the line, you can, if you have precision timing, you can find where the fault happened much more quickly than sending a helicopter down the line. So I have one other major topic. If we could go to the next slide, please. So time, there are several industries that have been using time for historically for some amount of time. Precision timing has been important in several industries, such as broadcast and other industries, but automotive vehicles, for example, have precision timing around the vehicles, but data has been transferred through separate channels, and this has created very complex systems. Combining these into one channel, such as an Ethernet channel, it requires new technologies because data and timing are very different. They don't work together very well. Data is best decoupled from the physical layer. Timing is best tightly coupled to the physical layer, and both are being sent over networks. So there are new technologies that have been developed to allow the marriage of these two rather dissimilar technologies. And it is solving the complex wiring of many systems. Next we'll move on to our first presenter. I'd like to introduce Joe Neal of Microchip Technology. He is a technical specialist. Joe, over to you.
Yes, thank you. Thank you very much, Mark. And first of all, I'd like to thank the ATIS team for inviting Microchip here today. And also a special thank you to Mark Weiss, who's been a long time mentor to the timing community and always encourages us all to think outside the clock, if I can put it that way. A couple of caveats for this part of the presentation. It's not going to be technically detailed and heavy 5G engineering. I hope it's thought-provoking, which is what it's really intended to be. So why do vehicles need precise positioning? Fundamentally, we're talking about collisions. I know that this statement at the bottom of this slide it makes us laugh now. Trains should not have been at the same place at the same time. But it was actually a revelation in the early 1800s that location of moving objects was not centered only in the moving object itself, but also related to synchronization between places outside that object and between the objects themselves. So if you look at here, for example, the problem was defined by, look, we've got two different places. One is at 11:10 or 11:50, I beg your pardon, Bristol. One is at 12 o'clock. And when we send trains between these two places, there is no synchronization between the three entities, the moving object and the two fixed places, the two fixed clocks. And therefore, we had a 10-minute time error, which meant that trains could be 10 kilometers from where they were expected to be. So understanding the relationships overall globally between fixed places, location, movement, position, and time was quite an eye-opener at that time. Now, when it comes to today, well, actually, it's not much different. we have different dynamics. We have many moving objects. They're not on rails. It shocked people in the 1840s that objects on rails could actually we didn't know where the location was. But today we take it for granted. Let's have a look what's happening here. We see we're in 3 vehicles involved here, right? So the white van just narrowly manages to miss a static car pulled over on the side. This tracking vehicle also manages to miss the moving of the static object. So what do we actually have here? We have, first of all, a lateral and longitudinal awareness. So we have 2 objects that are moving. Both of them have longitudinal awareness of what's going on in front of them, if you like, and both of them have lateral awareness. The white van you saw made an amazing escape, if I could put it that way. And if I can just play this again, well, and it won't play again, doesn't matter. So let's move on to what for the vehicle, what we're actually seeing. We understand that vehicles cover relatively large distances, even at low speeds, and this is well known. And if you look at the National Highway Traffic Safety Administration, it actually comes up with figures that tell us, look, if you have a non-autonomous vehicle, which is level 1, you have to have a longitudinal and lateral positional accuracy at 100 kilometers an hour, which is stated here in the table. And we have a total processing time from the point of understanding where we are on the road of 100 milliseconds. But if you look at level 3 and above vehicles, then we see that there's a very considerable more tightening of the parameters. So that when you're at a level 3, which is the first level of autonomy, you see that now we're talking about 2 to 5 centimeters of longitudinal awareness at 100 kilometers an hour. Start to think what that means. This means that in less than 10 milliseconds or up to 10 milliseconds, we have to know exactly where we are in relation to other moving objects within a couple of centimeters. But what we don't have from the NHTSA, and this is something which I'd like to show you here, is any notion of how this is synchronized. We have statements of latency, we have statements of lateral and longitudinal awareness, and even when we're looking at the different levels of automation, we have references to ADAS, advanced driving system assistances, but we don't have any notion of time. We don't have any notion of synchronization between the moving objects. And by the way, just I thought I'd call this out, that the Tesla is still only considered as partial automation. I know the marketing is different from that. Now, what is missing in these last couple of slides? What is missing is that you don't have this 200-year-old notion of a global connection between what is static and what is moving. We have the notion of proximity, longitudinal, latitudinal awareness, and we have the notion of how much time it takes to process information, but we don't have a global statement of how we synchronize these globally. So let's go on to the next slide. Trying to get it to move. So there's a little bit of a lag on the slides, guys. So let's talk about control planes. So in a single vehicle, one car, you have an individual, a big brain, basically, in control of that vehicle. It's a level 1 or level 0 vehicle, what we have today. And that control plane is entirely hermetic. It's centered in the vehicle. It's the person driving the car, basically. To try to move outside that, because we understand the dangers of that, we saw it on the previous slide with the van almost colliding with the static vehicle. We're trying to move into a cloud-based centralized vehicle intelligence. But the cloud today, despite the advent or the imminence of 5G connections, is far too slow and too imprecise in terms of the understanding of the location of the moving vehicle at 60 miles an hour relative to every other vehicle around it, to actually handle the movement and control within the required delays that would enable 2 to 5 centimeters of proximity control. So what the overall autonomous vehicle community is looking at is how can we distribute intelligence around the vehicles and have a self-coordinating group which would augment the individual intelligence and the centralized intelligence and offer security, safety, but at the levels of granularity which appear at the moment to be unattainable with a couple of centimeters. Are there technologies that can help that? We're going to look at some of those. So what are the aspects to in-vehicle timing to vehicle timing? There are basically 3 major aspects. You have timing and clocks inside the vehicles, an enormous number of protocols and standards, a lot of them proprietary. You have timing from the sky, so satellites relative to universal time, but we know that there are some problems with these signals. We'll see that in a second or two. And then we have the relative position of moving objects relative to other moving objects and to static objects on board sensors. And today we're loading vehicles up with sensors. Now, in vehicle timing, there are lots of proprietary timing functions and clocks in cars. In fact, Microchip delivers a lot of these systems, ECUs, IMUs, media, infotainment, navigation systems. All these have different clocks. And these clocks are not necessarily synchronized inside the vehicle. So we start with the idea that, it might be good to have a centralized clocking system in a vehicle. That's one thing that we could look at. And everybody is looking at that from the point of view of time-sensitive networking inside the vehicles. But once you're in the vehicle, how do you propagate that around the vehicle? Today, there are up to 80 different networks in a vehicle, all of them relying on different types of clock, not necessarily a centralized clock. Some of these are deliberately separate because they're control systems for safety, etc. Some of them are not. And all of them use these onboard hardware clocks, not necessarily linked to GNSS. GNSS is almost like an afterthought for a lot of vehicles because it's not reliable enough. Let's have a look at GNSS. Now, the DOT tested GNSS a few years ago inside New York City, and they were shocked to find that in practice, GPS was ineffective. In fact, it was 80% of the time unavailable. And this developed the whole notion of urban canyon, which is something that I think now that we understand throughout the industry. Urban canyons are a classic effect of high-rise buildings and of the weak signal that is coming from the sky. And of course, we have tunnels, parking, interference, and now we're seeing more and more possible jamming, etc., from the malicious community. What about sensors? So sensors themselves can be impacted by environmental considerations. They do give excellent proximity for other near objects. But when you look at these 3 aspects of timing, the in-vehicle timing, the sensors that are also attached to the car, and the GNSS, the thing that's really missing, the one item that's missing here is synchronization. And we seem to have forgotten this 200-year-old lesson that, in order to control moving objects, we have to know where they are and we have to have a point of reference. In other words, we solve different instantiations of timing, in particular position, navigation, and time by synchronizing clocks. We synchronized London to Bristol. And we built satellite systems, put them in the sky to send information to moving entities. We engineered oscillators to be more precise, more reliable, work at different temperatures. Now we need to deliver these timing systems more accurately across all moving vehicles, moving at all times relative to each other and relative to fixed points of reference on the ground at any speed. In other words, we need all vehicles on the same precise time in a dynamic local time scale. And I'm calling this, instead of universal coordinated time, vehicle coordinated time. So how do we do that? Well, first of all, we're going to downsize the timescales. Timescales are typically being global or national, but it can be regional, it can be local, it can be a city block, it can even be a building. So if we think of a micro timescale, we can now start to think of, well, how do we do timescales today? We do them with satellites in the sky. What about a micro timescale? We can do that with satellites effectively on the roof. We can use beacons at the street level, populate the street with what we may call a micro PNT mesh, which becomes a micro timescale. And how do we do that? Well, I'm going to move on to one more slide and show you an idea. You have a canopy of GNSS, and we can tie these micro PNT clocks, micro position, navigation, and time clocks that are deployed on street poles or buildings. We can actually have line of sight to GNSS. Therefore, we can tie the whole system to UTC and have a universal time constant for every vehicle in the street. But by putting the proxy PNT clocks local and low and putting them everywhere effectively on street poles, we can now avoid the urban canyon and ensure that access to that information is fast and reliable. If I go up a slide, you'll see what I'm talking about. So here we move GNSS from 20,000 kilometers to a close proximity. So we have a canopy now of things in close proximity, distributing fast, precise PNT information with less interference, instantaneous location information, and positional self-awareness for the vehicles. One of the things we have to think about too, which is absolutely critical in this environment where you have many moving vehicles that are quasi-chaotic, is 9 nines reliability, not 5 nines reliability. And one of the problems with sensors is that you're near with sensors, but you're not near enough. There's not reliable enough to give you this kind of reliability. And how would we deliver these signals from the micro PNT to the vehicles? You can have RF chips in the vehicles instead of having extremely compute intensive GPUs that are trying to recalculate instantaneous maps. You can just range between vehicles continually hundreds of times a second and calculate relative position. This gives you picosecond level of granularity, which translates into sub-centimeter granularity at all speeds. And the processing time in the vehicle then has a bit more elasticity. And you have RF chips of the same kind in the PNT, with vehicle to PNT communication using the same kind of technology. But remember, you also have GNSS information in these clocks. So the vehicles don't only know where they are relative to each other, they know where they are relatively to a global known reference time and location. In other words, you are synchronizing globally. So this is my last slide. In trying to bring GNSS closer to the vehicle and make it much more reliable so that we have faster access, ultra precise location at street level on lampposts, for example. We have micro timescale linked to UTC, a meshed coordinated timescale, not isolated individual clocks in each car, but a synthetic clock, if you like, a dynamic moving clock, which can coordinate multiple vehicles within a well-informed area. We can provide, therefore, security and protection for the PNT signal with vehicle-to-infrastructure communications that are synergistic with 5G RF, synergistic to broadcast and Wi-Fi, and also can use cloud information by downloading edge compute information to these PNT instances. So we can have precise, coordinated timing for all the in-vehicle clocks, a UTC reference for all the vehicles at the same time in the area, a vehicle coordinated time, which is a local timescale, and that local timescale can ensure location information, traceability, and security within the parameters required of the 2 centimeters of lateral and longitudinal awareness. And you have a clock-to-clock communication with the cloud.
Okay, well, thanks. Hello, everyone. My name is Anand Ram. We lost Joe there, so I will introduce myself. Before I do that, I'd like to take the opportunity, if I could, to let you all know that we are going to do question and answers at the end of this webinar. There is an opportunity to enter your questions on the control panel. So if you open the control panel for the webinar to the right of your screen, you will see a section in the window called chat. Open that and enter your questions by text. We'll answer, get your questions at the end of this webinar. So thank you for joining us. My name is Anand Ram, and I work for Calnex Solutions, and we make test and measurement excuse me, test and measurement equipment for timing and synchronization. So my part of the presentation is I'm going to be looking at the area of timing in data centers. As we all know, the infrastructure, global infrastructure of data centers is significant in our day-to-day lives and operations, and we are seeing the need to see the precision timing being distributed across these data centers. I'll take it, and what we're going to be looking at first and foremost is what are some of the drivers for the precision timing in these data centers across the world, and then also some of the technologies and methodologies being considered for deploying timing. The first driver, as Mark mentioned at the start of this presentation, is really that data as well as databases need to be decentralized. Computing and computing power also needs to be distributed. You know, there's a statement here from Gartner that's saying, you know, by 2022, 70% of data is created outside the data center or cloud, up from 40% today. That means that the data is not just being stored everywhere, but it's also being created everywhere. And one of the fundamental problems this presents to anybody in the data center or cloud environment is how do you then transport that data? Because transporting data is what costs money. Storing data costs money, obviously. It needs physical infrastructure to store it, but transporting the data today is probably the most significant cost associated with that data. So the cost factor is one, but secondly, if we need data everywhere and we need the compute everywhere, I cannot wait. Many applications today demand that data be updated and be available instantaneously. So I can't have data being distributed and also have low latency with that data if it is distributed. So those are some of the challenges we have to address. The data and databases and the computing needs to be distributed, but at the same time, we can't distribute it and compromise the availability and latency of that data. The fundamental requirement when you distribute data around the world is that you need that data to be correlated with respect to time. The basic question you're answering is when you update data or you have data interaction, we must know is data newer or older. In addition to that, if you're doing any analytics, and increasingly things like machine learning and artificial intelligence will be performing, not just performing analytics, but using those analytics to make decisions and control, we absolutely need to know the sequence of data that we're processing. So time correlation and time synchronization of data is important, and it's important when, even more important when that data is distributed. One of the other drivers is, and remember I talked about the cost of transporting bulk data. When you are able to synchronize data and know which data is older and newer, there's less of a requirement to transport data and compare data around the world. Lower rewrite requirements for that data itself. So if we can be sure that data storage and creation is being synchronized on a global or even national scale, then there is less of a requirement to transport that data, and therefore less data needs to be transported, meaning less cost associated with that. And of course, if we don't have good synchronization, the incorrect sequencing of data can lead to some consequences, which we'll talk about a little bit more in a while. If you get incorrect analytics or incorrect processing of sequence of data, obviously there's going to be disputes, things like incorrect billing, but more critically, if this AI is being used for critical applications, wrong decisions could lead to pretty critical consequences. And of course, as I mentioned before, if the data is not correctly or accurately synchronized, there is a requirement for more comparison and rewrite of data, and therefore a greater requirement to transport more data, which of course means more money. Getting into more detail, another driver for accurate timing within the data center environment is really the financial industry. So finance is an industry where synchronization has been a fundamental requirement for a while. Why? Because today, financial trading happens not by traders human traders on the floor, but predominantly by computers running algorithms and programs. These transactions obviously need to be timestamped. We need to know which transaction happened first and which happened next. And now the requirement for the timestamping accuracy is being mandated by regulators. So I've mentioned FINRA here, as well as the SEC, and the SEC TAT stands for Consolidated Audit Trail. It's a requirement from the Securities and Exchange Commissions here in the US. MiFID II is a European directive that actually came into force in January 2018. Again, these are regulators starting to mandate the accuracy of timestamps used in the trading environment. Why? Because cause-effect forensics, as I call them, if something goes wrong, regulators need to go into the records of financial trading and determine, did event A cause event B, or did event B cause event A? And of course, in order to know that, we need to know which happened first. And the sequencing of that data requires accurate timestamping. If you have accurate timestamping, you're able to more deterministically know whether event A happened first or event B happened first. So that's one of the big drivers in finance, particularly with the requirement to do forensics and be able to determine the correct sequence of that data. So we need timestamping, we need accurate timestamping, but remember that the greater the volume of the data means the greater the accuracy of the synchronization that's needed. If you have one trade happening per second, you need synchronization that's at least twice as good. You need to sample twice as fast as the fastest event. And so you need 0.5 seconds of synchronization accuracy. 1,000 trades per second means you need 1,000 times more accurate synchronization. You need half a millisecond of synchronization. And so the greater the volume of trades, and of course we know trade volume continues to grow in the financial community. The more trades you do, the more money you can make, of course, potentially, and of course the more money you can lose. But the greater volumes of trades means it's a driver for greater accuracy for synchronization. And that synchronization in general in the data center comes originally, as we've seen before, from GNSS, but also from the trading network, the data center trading network. If you have accurate synchronization in that network, the greater the accuracy of that synchronization, the greater the budget for the processor and software that's running on these machines that are doing the trading. And of course, if you have accurate synchronization designed into your network, that then becomes documentation to provide to regulators. So for example, a trader that's challenged on a financial transaction can produce documentation showing that accurate synchronization has been designed and deployed in their network. So the financial community is another big driver for synchronization within the data center environment. And of course, the consequences are pretty clear. If you're unable to show accurate synchronization of timestamping, you could be subject to potentially very large fines, and we've seen some examples of this in recent history. And then the third area I wanted to look at is really ideas that many people haven't even thought of. You know, accurate synchronization could be enable a toolkit for new services in the data center environment. Things like better utilizing bandwidth, as well as things like queue control, to perform more intelligent and efficient routing of data. Remember this point before about a cost of transporting data. If data pipes get crowded, you can spend money to make the pipe bigger, but that is a very one-dimensional solution, which is not very popular. And of course, so people are looking at ways of more efficiently and intelligently managing and optimizing the transport of data. So if you're able to synchronize two endpoints of transfer of the data, you can use techniques to do things like queue control management and optimize the bandwidth. So more accurate synchronization could lead to more optimization of data transport, which of course could lead to savings. And coming back to events, which events happen first? Things like microbursts. Microbursts are issues in the data center environment. They'll spend a lot of time and money trying to figure out why they happen, when they're going to happen, and so on and so forth. But in order to analyze and do forensics when they happen, you can actually use, if you had accurate timestamping, you're better able again to same concept as the financial industry to determine did event A happen first or did event B happen first. By correlation, you can and establishing the sequence of events, you can then get the information about why something happened and take action to try and avoid it in the future. And Mark also mentioned that the infrastructure for 5G in the future is going to move from telecoms switched infrastructure to servers in data centers and a whole bunch of edge computing. So the infrastructure for the 5G network is going to look more and more like the infrastructure today for a data center. And as we know, 5G as a radio technology needs accurate timing. So obviously, if the data centers had timing infrastructure, that is a big enabler for 5G radios as well as its services. And of course, if we don't have accurate synchronization, bandwidth utilization isn't optimized, leading to more spend. It's difficult to do correct root cause analysis and take corrective actions. And of course, if you don't have timing in 5G, it just doesn't work. So what's new? Why? I thought we had timing in data centers today. And in fact, those of you in the data center environment know that time is distributed and does exist in data centers today. In fact, that's done with GPS or GNSS and a protocol called NTP. Why do we need a precision timing protocol? So NTP today is used in data centers. It's used for applications that need tens or hundreds of milliseconds of accuracy. If you need a 1 second event correlation, for example, if you only need to know to the granularity of a second when something happened, then NTP is good enough. You know, things like billing, for example, or even a Facebook update in Singapore, making sure that that's correlated with a Facebook update in London, a few seconds is absolutely fine for that. So everything that I've talked about up to now, the correlation and the sequencing of data, if you're happy with a second or a few seconds, then NTP is good enough to do that. And NTP is very widely deployed in the data center world today. So 100 milliseconds, a second is good enough for many things. 100 milliseconds is good enough for many things, but for infrastructure where we are trying to use accurate synchronization to enhance efficiency, 100 milliseconds gives some efficiency, but a microsecond enhances that efficiency. The other aspect here is that GPS, GNSS installations in data centers are notoriously trouble-prone. GPS is installed all over data centers. If you drive across a data center, look up to the roof, and you'll see a whole bunch of GNSS antennas, usually very poorly installed, close to each other. And so, you know, you need a great deal of expertise to do correct GNSS installation. The installation issues, as well as cable, media, and distribution issues. So GNSS is a good solution. However, it does have its challenges. And that's really why PTP is growing in deployment in the data center. It also offers a path to wide area correlation of databases. PTP is widely deployed today in telecoms for synchronization across wide area networks, so it does give the ability to do that. It does meet a lot of the financial regulatory requirements. It's been deployed widely today in exchanges around the world in order to meet that. And of course, PTP, as mentioned during this whole presentation, is a path to offer some new services. And this is just an example of how PTP would complement current time distribution in a data center, where you could have GNSS or GPS coming to the data center, being distributed in the data center, but then PTP deployed across that data center switching infrastructure. So where you have things like the spine, leaf, and top of rack switches are PTP aware. They're called boundary clocks in this case. And then the network interface cards are the end clients or slaves on the servers themselves. So it's just one example of how PTP would be distributed across a single data center. And this is being done and deployed in many data centers around the world. So that was really my presentation on the use of PTP in data centers and some of its drivers and benefits. What I'd like to do now is I'm going to pass over to Nir Latha. Nir is the Senior Director of Product Management at Oscilloquartz, and he'll continue with the next part of this presentation. Nir, over to you.
Thank you, Anand. So Anand and Joe described a new emerging application which require time. And I would like to discuss two existing applications that use time for centuries. However, they now require a change in the way that the timing is provided into these applications, as well as allow a more accurate time that enable a new application within these use cases. And these two applications are the broadcast industry and the power utility industry. Next slide, Katie. So before we move to the actual requirements and see why accurate time is needed in these two applications, just to have a short reminder of how fast is 1 nanosecond. If we look at the blink of an eye, that's typically only 300 milliseconds, and for some of the applications, this might be enough. But as we move to new applications, we will see that the requirements are becoming tighter and tighter, moving from milliseconds to microseconds to nanoseconds, and that require a different way of providing timing. And on top of that, there are new architectures moving from legacy dedicated synchronization interfaces into a modern IP-based communication, which change the way that the time is delivered within the applications. So going back to the requirements, we will see that in most of the broadcast and power utility, the requirements were in the level of milliseconds, and the new requirements are now becoming a sub 1 microsecond. Next slide, please. So let's start from power utility synchronization. As we look at some of the these applications, we will probably notice that these are critical infrastructure. You could all imagine what happens when we don't have power available, and such an outage or a blackout happened in 2003, and some of the lessons learned from this outage are related to synchronization. We can see a list of these lessons learned. First one is the need to have a better understanding of what's going on in our grid. Better time synchronization for digital fault recorders, phasor measurement units for better system level view, event time tag that are in the level of 4 millisecond accuracy, and a backup to GPS or GNSS that might not be available at all times due to jamming, spoofing, or even an antenna failure. So all these eventually require a better timings that will allow us to better understand what's happening in the power grid. Next slide, please. So if we look at the way that the requirements evolved, the original requirements were in the level of 1 second. These were needed for bulk metering and customer premises metering. As the requirements evolved, there were a need for a better event recording in the level of 1 millisecond. And now we are talking about the smart grid, some of the applications that Mark mentioned, such as fault localization and synchrophasers that require a 1 millisecond accuracy. And we can see the corresponding technology, starting from a dedicated iRig interfaces, moving to NTP, and eventually to PTP, that able to provide this level of accuracy. Next slide, please. So if you look at the substation today, we will notice that there are a different type of technologies used within the substation. Some of them are legacy technologies that require dedicated cables to provide synchronization, such as iRig-B or 1 pulse per second interfaces. And on top of that, some of the newer applications are using NTP and provide a millisecond level of accuracy. The challenge with this architecture is it's very hard to scale, very expensive, and as mentioned earlier, require dedicated cabling to each of the end application in order to provide the timing. On top of that, the accuracy, which can be delivered using these legacy interfaces, are limited, and in most cases cannot achieve the 1 microsecond accuracy needed. Next slide, please. So as we're moving towards today architecture, the legacy clocks are now replaced by a new PTP Grandmaster clocks. Next slide, please. You could see the PTP Grandmaster clocks. They are supporting both the legacy interfaces that are needed for backward compatibility purposes, but on top of that, they are providing accurate timing using the precise time protocol 1588. These are typically connected over a PTP aware network. These are typically substation switches that incorporate transparent clock capabilities that allow to provide very accurate timing to the different end devices who are now connected over Ethernet and IP infrastructure. Another very important point is to be able to monitor the quality of synchronization within the substation. As mentioned earlier, one of the main objectives of having an accurate timestamp or accurate timing is the ability to better monitor the quality of signals within the substation. And in order to be able to monitor signals properly, we first need to monitor time itself. So there is a need for continuous monitoring of the sync or the quality of synchronization within the substation. And this can be done by comparing clocks. For example, we could compare the Grandmaster clocks recovered locally from GNSS versus another accurate clock connected through the network to a core sites where an EPRTC, Enhanced Primary Reference Time Clock, is located with a cesium clock that allows us to have a very stable and accurate time. And using PTP, this could be provided into the Grandmaster clock and can be used to monitor the quality of the clock generated locally. It can also be used as a backup to the local GNSS in case there is a local outage at the substation. So this architecture allows both accurate delivery of time within the substation. It also allows a backup using the network backup, and also provide monitoring by comparing two clocks who are not co-located. Next slide, please. The next application is also an application who used synchronization for a long time, and you will see that there are a lot of commonalities between the power and broadcast applications. Both of them use synchronization, but they are now moving to all IP. Next slide, please. So the story is very similar. The broadcasting used to use dedicated clocks, sync pulse generators. These sync pulse generators created a clock typically from GNSS, and this clock was propagated within the network through a dedicated SDI interface. This serial digital interface was carrying both data and clock over a dedicated cables that were eventually connected to the cameras, to the recorders, to the frame synchronizers, and that's how the timing was distributed within the broadcast application. As we move to a more simplified model based on IP, we are now using a PTP, a Grandmaster clock, which is using a special profiles designed for this application. The Grandmaster is connected typically over a network, a short network of PTP-aware switches or routers that are distributing time into the different end applications, which require typically a sub 1 microsecond accuracy. So you could see how the requirements are very similar. Moving to IP is also similar, but the PTP profiles who are used in this application are tailored for the broadcast use case. Next slide, please. So if we look at the transition from legacy SDI transport to IP transport, we will see the use of a dedicated PTP profile. However, once this profile is used, It allows to evolve toward IP network with the flexible processing of video and audio. The modern environment include a lot of flows, both video and audio, are running in parallel. For example, high definition MPEG require 4 video streams and 5 audio streams, all transported simultaneously, and eventually needs to be resynchronized. So this type of scalability require the use of IP, and eventually the use of PTP allows us to synchronize all the end applications and to retime these streams back together where they need to be multiplexed and broadcasted. Next slide, please. So if we look at the transition from the legacy synchronization into the modern PTP-based synchronization, we will see that there are 2 steps here. The first step is to solve the problem within the broadcast network. The use of PTP also allows us to provide a very compact, small-scale grandmasters. Some of these applications, such as mobile broadcast tracks, are very restricted in terms of real estate, and they need a very small and cost-effective PTP grandmasters. These can be used locally with the help of GNSS to recover very accurate time, and then using the 2 audio and video PTP profiles to distribute time within these applications. And the second step would be to create a backup using the network. Eventually, these applications are connected through an IP transport network. And again, we could locate a centralized, redundant, high-performance grandmasters that can communicate to these remote sites using a sync-aware network devices that are typically transparent clocks or boundary clocks. And one of the use cases is to use the power profiles locally, the broadcast profiles locally, and use the telecom profiles over this IP transport network. So one of the functionality needed by these local grandmasters is the ability to translate between telecom profiles who are used in order to connect to the remote grandmasters, while translate these telecom profiles into broadcast profiles who are used locally. Next slide, please. I think that's all for today. Mark, back to you.
Thank you, Nir. I think we've had a number of really interesting talks about some of the issues involved with precision timing and why it's important today. I think we have time for a short question. There's been questions about timing security and timing safety that really are relevant to any of the speakers. I wonder, Anand, if you're available to address this question, for example, in databases and fast trades where there are high frequency traders or AI is in place. Can timing be attacked, and how safe is the timing?
Yes, Mark, I'll take that question. Good question. Security is actually a very big question for precision timing. The fundamental challenge is most techniques dealing with security today, things like encoding or encryption, really affect timing. So if you encrypt and decrypt something, you take away deterministic timing very often. And so they're kind of almost conflicting with each other, the need for security and the need for precise timing. And so there's a lot of work going on in the industry. The next revision of 1588 PTP is going to include a section on security. It's a framework rather than the be-all, end-all answers, so it's still work in progress. in answer to your question, Mark, yes, security is an issue. There are lots of techniques being discussed today. What we see happening with security initially is obviously some security can be maintained. There is already security inside, for example, financial trading by it being a closed environment. So if you have a closed network and your timing is only being distributed within that environment, it's reasonably easy. You know, whatever you do to protect the data is the same thing that you do to protect the timing within that ecosystem. I talked about timing being available in wide area networks. That's obviously, and particularly in data centers, that's going to be a lot more challenging to protect against. So initially, timing isn't going to be used in those environments for anything that's critical enough to to have a huge consequence. So it's work in progress. In answer to your question, Mark, it is a concern. There is work being done and discussions being had, and there are also implementations within closed or contained systems on how you protect them.
Thanks, Anand. I think we should move toward closing at this point. Let's see, the next slide, please, Katie. I'd like to thank all the attendees for coming. I'd like to thank Addis for organizing it and all the speakers. There is a conference that's behind what we've talked about today that you can hear much more about timing and synchronization issues. I think what we've done today is really touch on some very complex ideas and questions, and much is happening. A very, very active community that's producing timing in many different sectors and in many sector independent ways. As you can see on the screen, I'd like to invite you all to go to the website, wstsconference.com, and explore the agenda that's coming, and welcome to the workshop on synchronization and timing systems in May. And now for the closing slide, I do want to thank you all for attending, and all registered attendees will get a follow-up email with links to a recording from the slides and this presentation. Thank you all, and have a good day.